Okay, what we're going to do now is try to find what does the voltage on the resistor and the capacitor look like between those two extreme cases. So we need to get a time-dependent equation to show what's happening in this circuit as time goes on, as this capacitor charges up. And very simply, we're going to get a differential equation by doing a Kirchhoff loop rule. Okay, so I've got a battery here with the positive terminal on the left and the negative terminal on the right. I know current is going to come out in this direction, so let me go ahead and mark the high and low energy side of the resistor and the capacitor. Well, the resistor is going to use up charge in this direction, so we got the high energy side here and the low energy side here. For the capacitor, which side are the positive charges going to accumulate? Well, positive charges are coming from the positive end of the battery. So here we have the high energy side, it's getting positive charges. Here, the low energy side getting negative charges. So we've got these marked. Now let's go ahead and do a loop. I'm going to use the battery to help me with my direction of my loop. My battery is going this way, so I'm going to go ahead and do a clockwise loop. So let me take my finger in a clockwise direction. As I go through the battery, I get a raise of V. Low side to high side is a raise of V. I go up to the resistor, and it looks like I'm going from high side to low side, so that's a drop of IR. Again, I don't know what that current is right now, but I know the voltage on a resistor is I times R. And when I get to the capacitor, I go from high side to low side, so that's also going to be a drop. But what is voltage on a capacitor? Well, I know CV, we're charged up, so the voltage then would be Q over C. So this is going to be Q divided by the capacitor C, and this is equal to 0. Of course, the sum of the voltages around a closed loop has to be 0. So I started with a Kirchhoff rule. I don't see any calculus right now, but I want to write a differential equation. And I tell you that there is actually a hidden derivative somewhere inside of this equation. So V is equal to V minus IR minus Q over C. There is a hidden derivative here, and that hidden derivative is in the current I. Remember that I is how many charges are passing a area, a cross-sectional area per time. So this is dq dt. So we actually have now a hidden derivative, and that is V minus, I'm going to write this as R dq dt. That is replacing current I with a derivative. And that derivative is related to this Q right here, the Q that's accumulating on the capacitor. Okay, so what I want to do now, since I have dq dt, let's aim to get Q as a function of time. Let us get charge as a function of time. So of course I need to isolate the, I'm going to isolate the differential equation, so the first order derivative right here, dq dt, by moving the R dq dt to the other side because it's got a minus here. So let me say V minus Q over C is equal to R dq dt. Okay, the next thing I'm going to do is divide everything by R. So I have V over R minus Q over RC is equal to dq dt. And now I want to make sure that the rules for integrating are satisfied. The first thing I need to do is attach everything to a small factor by multiplying by dt. So V over R minus Q over RC times dt is equal to dq. So the first rule is satisfied, but you'll notice the second rule, which says each variable needs to be attached to the correct small factor. Well, unfortunately, this Q is not attached to the correct small factor, and the only way to get it over here with dq is to divide by this entire term. So that's going to leave me with dt is equal to dq all over V over R minus Q over RC. And now I'm ready to integrate. But this is not a pretty integral. And it's not an integral that I want to try a substitution with. I want to make this look like an integral that I already know how to do. So I go to my equation sheet and I look at some of the integrals that are on there on the small integral table. And I know this guy is on there. That's 1 over x plus a dx. That's what I want to make this look like. I know I have Q here on the bottom. It's to the first power. I'm confident I can make it look like this, 1 over x plus a dx. And we know the integral of that is just the natural log of the absolute value of x plus a. So if I can make this integral look like that, then I'm prepared to do it without substitution, without going through, the U, all the stuff that's really going to challenge me on the AP Physics exam. So let me try not to do as much math, as much calculus. Let me try to just make sure I understand the physics here. So I'm going to pull out, definitely pull out a minus 1 over RC. Pulling out a minus 1 over RC is going to give me that plus Q that I need right here, plus Q. So let me, on the bottom, integral dt is equal to the integral of dq. I'm pulling out a minus 1 over RC, a minus 1 over RC. And when I go ahead and multiply here, I'm going to get V, looks like V times C. Would you agree with that? V times C, because if I multiply this by 1 over RC, the C's would cancel, and that'd leave me with my V over R. But because I pulled out a minus 1 over RC, and this was initially positive, this guy is now a negative, so minus VC, and I pulled out a minus 1 over RC, so this guy just becomes plus Q. So just to make this look a little bit better, let me go ahead and multiply by this 1 over minus 1 over RC. Well, this is a fraction in the denominator, right? This is a fraction in the denominator. So this is like having 1 over integral dt is equal to integral minus RC dq all over Q minus VC. Okay, and I'm almost ready to integrate, except I want it to look as much like this as possible. So I want that 1 in the numerator. And I'm going to do that. I'm going to achieve that by dividing by minus RC. So that gives us minus 1 over RC integral dt is equal to the integral of 1 over Q minus, and I'm going to write this actually now a little bit more suggestively as CV. Okay? Well, it looks like I'm ready to integrate, except that I haven't given you the integration bounds. So I want this to be, if it's with respect to charge, I start out with an uncharged capacitor. So I know at the beginning of time, I have no charge. And sometime later, not a specific time later, sometime later, then I would have Q as a function of time. So that's specifically here, this is Q as a function of time. This is not the total charge, because I'm not saying that I'm going to let it go for an infinite amount of time. I'm saying sometime later, what does the charge look like? That way I can get what that curve looks like of the charge, okay? So the integral on the left is pretty simple. Minus 1 over RC is a constant. Integral dt with evaluated from 0 to t is just t. So I have here minus t over RC. That guy's not bad at all. But again, this guy, you'd have to do a substitution to get this integral, but I know from my small integral table that the integral of 1 over x plus a is the natural log of the absolute value. So here I'm going to say natural log of the absolute value of q minus CV. Okay, so hopefully everything up to this point you understood and it made a lot of sense. I'm introducing you to the point where most people are going to make a mistake and they're just going to move on from here. Do not forget to evaluate from 0 to Q. A lot of times that 0 term doesn't contribute. You notice that I kind of carelessly did it on the left side. That 0 doesn't contribute. Here it is going to contribute. It's really, really important that you evaluate it. So minus t over RC is equal to ln of, well, when I evaluate it at Q as a function of time, I get Q as a function of time minus CV. Again, absolute value, minus the natural log of, when I put in 0, notice that I still have a term here. So that's really, really important. Don't make that mistake of just moving on carelessly, okay? Same thing we had to do when we did terminal velocity. This equation, this integral, this mechanics should look very similar to terminal velocity for something with air resistance or moving in a resistive medium, okay? All right. Well, I know when I have here a subtraction of natural logs, I know that's the same thing as a natural log of the quotient. So minus t over RC is equal to the natural log of Q as a function of time minus CV all over minus CV. And I want to get out of that natural log. And I get everything out of the natural log by e-ifying both sides. So I'm going to raise both sides up above e as the exponent on e. So I have e to the minus t over rc is equal to, well, inside of here I get q as a function of time minus cv all over minus CV. Let's go ahead and solve for Q as a function of time. So I'm going to multiply by minus CV. So I get minus CV e to the minus t over RC is equal to Q as a function of time minus CV. So last thing we need to do is add CV to both sides. I get CV minus CV e to the minus t over RC is equal to the charge as a function of time. But I see this CV term, and I'm going to pull it out because it looks awfully familiar to me. Let me pull it out and say 1 minus e to the minus t over RC. The first thing you should notice is that I have a 1 minus e to the minus t over RC. Now, I told you this was one of the two equations that I need you to memorize. I need you to memorize what e to the minus x looks like and what 1 minus e to the minus x looks like. This e to the minus x is an exponential decay, right? Starting out with a high value and it's decaying towards 0, or it could be decaying towards some value here. 1 minus e to the minus x we called an exponential approach, and it is approaching some value. So the first thing you should notice is that this is an exponential approach. It's approaching some value, and that value is going to be this coefficient right here. But this is a constant. It is the capacitance times the voltage. And if you remember from our loop rule, that was the voltage of the battery. So when the voltage on the capacitor is fully charged up, when the voltage is equal to the voltage of the battery, CV is just Q total. So you'll notice then that makes sense that the charge as a function of time is approaching Q total. Okay, so this is what we expected at t equals 0, the charge should be 0. At t equals infinity, the charge should be CV. So we can say charge as a function of time is equal to the total charge times 1 minus e to the minus t over RC. Now, 1 over RC, this guy right here, the RC, this is what we call tau, the time constant, okay? And you'll notice that in varying the resistance and the capacitance, you can vary how long this thing takes to fully charge up. The higher the resistance and the higher the capacitance, the longer it takes to charge it up. So this product of RC relates to how long it takes to charge the capacitor fully, okay? If you have a really low resistance, this thing charges up almost instantaneously. So this curve becomes a lot steeper and it goes up to Q total almost instantaneously. If you have a really large capacitor and a really large resistor, then you can really flatten this curve a bit. That's sort of a terrible joke there. But you can make this charge up over a lot longer period of time. And depending what your application is, you can play around with this time constant to get exactly what you want. But I'm not going to stop there, because I know that with Q, I can do so many things. For example, with Q as a function of time, if I just, let's say well, we know that Q is CV, so I could find the voltage on the capacitor as a function of time by just dividing Q as a function of time by C. And Q as a function of time is Q total times 1 minus e to the minus 1 minus e to the minus t over RC. And if I divide that whole thing by capacitance, well, what is Q total over capacitance? It's just V of the battery, or V total. So this would be V times 1 minus e to the minus t over RC. Does that make sense with what we said about the extreme cases? At t equals 0, the voltage should be 0. Plug in 0, you get 1 minus 1. So at t equals 0, the voltage on the capacitor is 0. At t equals infinity, you get the voltage of the battery, right? This guy, the capacitor, will shut down the circuit. There won't be any current in the system at t equals infinity. Okay, there are more things that we can get, time-dependent functions. We know everything about the capacitor right now. We know the charge and the voltage. How about, for example, the current as a function of time? Well, current, as we've said before, is just dq dt. So if I take the time-dependent charge and to do the first derivative with respect to time, well, let's go ahead and do that. Let's see. The derivative with respect to time of q total times 1 minus e to the minus t over rc, right? Let's take one derivative. Well, when you take the derivative of 1, you get 0, so I don't have to worry about that term. So I just have this term of minus q e to the minus t over rc, minus q e to the minus t over rc. When we take the derivative of that, we get, well, there's a minus q total here. You take the derivative, you get e to the minus t over rc times the derivative of the exponent. If you remember how to do derivatives of e, you get e to the minus x times the derivative of whatever the exponent was. And the derivative of this guy is just going to be minus 1 over rc. So this is times minus 1 over rc. And this should all be equal to the current as a function of time. Well, two minuses here are going to make it positive. So I get Q total. Let me bring out the RC. So Q total over RC, e to the minus t over RC. First thing you should notice, this is an exponential decay. Does it make sense that the current is heading towards 0? The capacitor is shutting down the system. And that makes sense. That's what we expected from the extreme cases. But what is this Q over RC? This is something that seems kind of familiar. Well, Q over C, Q total over C would just be the voltage of the battery, right? So voltage of the battery divided by R, e to the minus t over RC. But when the voltage of the battery is on the resistor, that would be the maximum current. So here our current as a function of time is some maximum current, which is when all the voltage is on the resistor. So I max times e to the minus t over RC. So this guy would be an exponential decay starting at V over R. Okay. Can we go anywhere from there? Well, let's see. We could say the voltage on the resistor as a function of time. We know voltage on resistor is just I times R. So if I have I as a function of time, multiply it by R. So here we have I max times R times e to the minus t over RC. But wait, what is I max times R? When all of the charge, the maximum charge is going through the resistor, that only happens when the voltage on the resistor is equal to the voltage of the battery, and there was no voltage on the capacitor at t equals 0. So here, e to the minus t over RC. So the voltage on the resistor as a function of time is this guy. It's also an exponential decay. So I'm going to draw then our four graphs that we have. We have charge as a function of time, charge on the capacitor, pretty simple. This was an exponential approach, and it's approaching Q total or CV, okay? We also have V of the capacitor as a function of time. V of the capacitor, well, it's also an exponential approach, and it's approaching V of the battery, okay? We have current as a function of time. Current as a function of time was an exponential decay, but it doesn't start at infinity. It starts at a value, and that value is our I max, or that is V over R. And the last one we have is the voltage on the resistor. It was also an exponential decay, so it looks like that, but it does start with a value, and it starts with the voltage of the battery. So these four graphs are something that you should be able to sort of conceptually come up with very quickly. But if the free response is given to you where you have to go through this, it's not a terrible amount of calculus, really. The worst part is getting your integral to look like something you know how to do. So get your integral to look like this, which is 1 over x plus a. And then the biggest misstep I would say that students make is forgetting to evaluate this here from 0 to q. Don't forget to evaluate, make sure if you need to write it out for all cases. Even with this one, I kind of carelessly didn't evaluate it at 0 because I knew it didn't add anything. If you want to be careful on the exam, evaluate it at every term. Okay? The next video will be discharging the capacitor, and you're going to notice it looks a little bit different than what we're seeing here.